Swayam Prabha. Digital India. Educated India.
Hello everyone. In the previous class, we had discussed about the classification of the rock mass, and in that one we studied about the classification system, that is Q system, and I mentioned to you that there are 6 parameters which are used to evaluate the index Q, and we saw the details of all those 6 parameters along with the procedure of to obtain their rating. So today we are going to discuss few other issues related to all those parameters, and then we will see how on the basis of this Q index one can define the rock mass, and finally we will see the application of this Q system. So as I mentioned that we had 6 parameters: RQD, JN, JR, JA, JW and SRF, and I mentioned to you that higher values of each of these parameters in the numerator, it represents the better quality of rock mass, and lower values of these parameters which are there in the denominator, that also represent the better quality of the rock mass. So we saw that there are various tables which can be used to assign the rating to each of these parameters. Just substitute all those values in this expression and one can obtain the index Q. So basically this Q is a function of these 3 quotients. The first one represents the block size physically, the second one deals with the interblock shear strength, because both these parameters JR and JA, they are related to the joint, that is the one is related to joint roughness and another one is related to joint alteration. So depending upon the condition of the joint, the shear strength will be decided. So that is why the second quotient decides about the interblock shear strength, and the third quotient, that is JW upon SRF, it deals with the active stress. So coming back to the first quotient once again, which is defined as RQD upon JN, it represents the rock mass structure and it is a measure of block size or the size of wedge which is formed by the presence of different joint sets. Larger is the RQD, bigger will be the block size, and therefore you will have this first quotient be representative of the block size. Higher RQD, lower JN, and of course vice versa. So this RQD upon JN, it takes wide range of values from 0.5 to as high as 200 plus. So it gives us the idea about the block sizes in a crude manner. In a given rock mass, the rating of JN could increase with the increase in the tunnel size in the situations where additional joint sets are encountered. So in such cases, it is not advisable to use a Q value which is obtained from a small drift to estimate the support pressure for a large tunnel or a cavern. So one needs to be careful about these issues, that when we go to the field, sometimes it is required to excavate a small size tunnel in order to have these observations. So in case you have such type of situation where Jn could increase with the tunnel size and where the additional joint sets are encountered, one should not rely on the Q value. It is more appropriate to obtain Jn in such cases from the drill core observations or a borehole camera. Second quotient is defined by Jr upon Ja. It represents the roughness and the frictional characteristics of joint walls or infilling material. The inverse tangent of this quotient, that is tan inverse Jr upon Ja, it gives us the idea about the residual frictional angle. In case if you have rough and unaltered joint sets, these will have higher values of this quotient Jr upon Ja as compared to that of the smooth slicken sided joints with clay filling. So better is the roughness characteristic of the joint, higher will be the value of this second quotient Jr upon Ja. Now the third quotient is SRF upon Jw. It is an empirical factor which describes an active stress condition. I mentioned to you that this SRF is a measure of loosening pressure during an excavation through shear zones and clay bearing rocks. Second was rock stress in the competent rocks, and the third was the squeezing pressure in plastic incompetent rocks, and this can be regarded as the total stress parameter. And if you recall our discussion in the previous class, when we were assigning the rating to this JRF, we considered each of these conditions in that table. Coming to the parameter which is Jw, a measure of the water pressure. Obviously, when the water is there, it will have an adverse effect on the shear strength, because of the simple reason that the presence of the water makes the effective normal stress reduce, and therefore the strength characteristic also reduces. So the adding the water causes softening, and there may be possible outwash in the clay filled joints. So this whole thing gives the reduction in the shear strength of the joints. Now we have obtained the ratings of each of these, and we can calculate the index Q. Its use is recommended for tunnels and caverns with an arched roof. In the beginning, I mentioned to you that each of these systems were developed based upon few researchers' experience in few areas. So like in case of the RMR system, where it was the experience on the shallow depth tunnels, similarly here in case of Q, the experience was for the tunnels and caverns with an arched roof. So when you have to use this Q system for other type of structure, you need to be careful, and you need to apply lot of engineering judgment when you use these system which were developed for some other conditions. So the use is recommended for this situation. Q is varying from 0.001 and it goes to become as high as 1000. As the value of Q increases, the quality of the rock mass also increases or it gets better. So, for the range of the Q varying between 0.001 to 0.1, the classification of the rock mass is exceptionally poor. For 0.01 to 0.1, it is extremely poor, 0.1 to 1 very poor, and likewise for 40 to 100 it is very good, 100 to 400 extremely good, and 400 to 1000 it is exceptionally good. Sometimes the condition in the field, they are such that you may not get one single value as a rating to be assigned to a parameter, rather it may be a range. So, in that situation, Q value will not be a single value, but then it may vary from Q minimum to Q maximum. So, in that case, the average value of Q which should be taken, that should be equal to square root of Q minimum into Q maximum. So, this value of Q should be used in the design calculation. There is the correlations which exists between RMR and Q. These are approximate relation. However, it has been seen that in some of the cases they work quite fine. So, two of these relations I have mentioned here. First one was developed by Biniawski in 1976 and it is quite widely used to obtain either Q from RMR or RMR from the Q value. So, this is given as RMR equal to 9 natural log of Q plus 44, and the second expression was given by Barton in 1995, where this RMR is approximately equal to 15 natural log of Q plus 50. So, there are few cases where you will be able to get the value of RMR but not Q, and then subsequently you may need Q, but you have already RMR with you. So, you can use these expression in order to get either of the quantity from one another, like RMR can be obtained from Q and Q can be obtained from RMR. Coming to some of the application areas related to this Q system, the first application includes the estimation of the support pressure, and these expressions were given by Barton et al. In 1974. So, the vertical roof pressure, that is given by this expression, and the ultimate wall support pressure is given by this expression PH, and you can see that here a term wall factor comes into picture. So, depending upon the range of Q, you can assign this value of wall factor as per this table. So, if the value of Q is more than 10, wall factor QW can be taken as 5 times Q, and if the range of Q is between 0.1 and 10, then this wall factor can be taken as 2.5 Q, and for the value of Q less than 0.1, it is equal to Q. So, you can find out the wall factor, just substitute in these expression and you should be able to get the ultimate roof support pressure and the ultimate wall support pressure. Some of the limitation while obtaining the support pressure as far as the Q system is concerned, they include with respect to SRF, that is the SRF is probably the most problematic parameter here in the evaluation of Q. So, it may be appropriate to neglect this SRF during the classification system and to assess its detrimental effects of high stresses separately during the analysis. So, we need to be careful that it should not happen that we are considering the SRF while calculating Q and also taking this effect in the analysis. One needs to be careful here. The next application is the determination of the modulus of deformation, and the related expression was given by Barton in 2008, where the modulus of deformation was defined by this expression, and this modulus of deformation which you get is in gigapascal. So, this should be less than the elastic modulus of the intact rock, which is obvious, and this expression is valid for the value of Q varying between 0.1 to 100 and the UCS of the intact rock varying between 10 to 200 megapascal. Once again I would repeat, when we discuss about the empirical correlation, then you need to be careful about the units of its parameters. Like in this case, this QC should be in MPa, and then only you will get this modulus of deformation in gigapascal, where this QC is the UCS of the rock material. For your ready reference, I have presented the typical values of the UCS for different types of rock in this slide. So, you can see that the first column gives you the idea about the type of the rock, and the column adjacent to that gives the typical values of the UCS in megapascal. The letters which are there in the bracket like I, S, M, etc., these include, like I stands for igneous rock, M for metamorphic rock, and S for the sedimentary rock. That means andesite is an igneous rock, basalt is an igneous rock. Similarly, here if you just see, gneiss is metamorphic rock, and shale, it can be sedimentary or metamorphic, and accordingly their values of the UCS have been given. Now, another thing which you must note here is this type of symbol that shows the large variation. That means, let us say that the type of the rock which is the metamorphic rock marble, and there is a average value of 100 megapascal is given with this sign. So, that means that around 100 megapascal large variation in the UCS of marble rock can occur. Okay. So, like that you can take the example here like quartzite, its value will be varying quite large, around 190. Similarly, for clay, hard clay, it is the 0.7 megapascal, and in case if you have silt, sand, approximately all these material, then you will have this low value of UCS. So, this gives us the idea about the UCS. So, when we have this UCS, we can substitute in the previous expression along with the value of index Q in order to obtain the modulus of deformation from the Q index. So, this is what that I wanted to discuss with you with respect to this rock mass classification system, which is called as Q system. So, what we discussed was that what all those three quotients they define physically, and then how the rock mass can be classified on the basis of the value of Q index, and then we saw some of the limitations related to this system, followed by various application areas. So, in the next class, we will learn about another classification system, which is geological strength index. Thank you very much.